Okay, this brings us to example 2.10, using multiple vectors in multiple directions and finding the resultant of them. Anyway, in this example, you've got four dogs that are basically playing tug of war with a toy, and it gives you the force and direction. It gives you the directions. Yeah, it gives you the force and direction for three of the four dogs. And then we're basically trying to find out what the fourth dog is, how much force and what direction is the fourth dog pulling in. So dog A pulls in direction that they're giving the direction in the form of an angle from the positive x-axis. I've drawn a little diagram here. They have a more artistic diagram in the book where they've actually drawn the dogs. I'm just calling the dogs A, B, C, and D because that's what their names begin with, rather than saying their full names. Anyway, they're measuring the angles from the positive x-axis, and dog A pulls in direction with an angle of alpha of 55 degrees south of east. That would be this right here. South of east just means basically it's below the x-axis, because traditionally the x-axis is the eastern direction if you want to deal in points on a compass. So 55 degrees south of east would be this angle right here. Dog B pulls in a direction with angle beta equals 60 degrees east of north. Well, north would be the y-axis, and so east of that would be basically to the left or toward the x-axis from the y-axis. And so that would be this angle right here. And so this is dog B. And dog C pulls in the direction of angle gamma equals 55 degrees west of north. 55 degrees west of north means in the second quadrant, basically to the left of the y-axis. Okay, so these are the axes. And then here's dog C. It also tells you that dog A exerts a force of 160 newtons. Newton is the SI unit for force, and it's a kilogram meters per second squared. And dog B pulls with a force of 200 newtons, and dog C pulls with a force of 140 newtons. So we know the magnitude of these vectors also. If D pulls on his end, and D is over here somewhere, we don't know what the force is. In other words, we don't know what the magnitude of the vector is, and we don't know what the angle is, but it's over here somewhere. If D pulls on his end so that the forces balance out and the center of the toy doesn't move, we're considering the origin to be the center of the toy. And so the center, so that if the forces are all balanced, that means that the center of the toy doesn't move. So in other words, D balances out the resultant of forces A, B, and C. Or in other words, D pulls with the same magnitude of force, but in the opposite anti-parallel direction to the resultant of forces A, B, and C. Okay, so what are the magnitude? And then the question is, this was kind of my interpretation. The question is, what are the magnitude and direction of dog D pulling on the toy? Okay, so again, as usual, we're going to define east as the positive x direction and north as the positive y direction. The first thing you would have to do in order to find the resultant of vectors A, B, and C would be to resolve those three vectors into their components. And then the resultant would be the sum of vectors A, B, and C. And D, that is the magnitude and direction, or basically the vector of dog D pulling on the toy, would be the negative of the resultant. Or in other words, another way of saying that would be the sum of vector D and vector R, that is the resultant of A, B, and C, would be 0, the null vector. before we can actually do this, we would probably want to recalculate the angles according to some common definition of angles. And it's customary to measure angles from the positive x-axis, or the east direction in this case. So we're going to call this phi for, or sorry, theta. Sorry, I got the line going vertically instead of horizontally. Theta for dog A is going to be negative 55 degrees because it's 55 degrees below the x-axis. So that would be negative 55. Theta for dog B is going to be 90 degrees minus beta, which was 60. So in other words, is 60 degrees short of the 90 degree mark, which would be the y-axis. So that's 30 degrees for theta B. And theta C, the angle for dog C, is going to be 90 degrees plus angle gamma. In other words, dog C is pulling with an angle 55 degrees beyond 90 degrees. And so that's 145. Now that we have the angles defined according to the customary way of defining angles, we can find the components. The x component of A is just the magnitude of A times cosine of theta A. That is the angle measured according to the customary methods that we just found. So that's 160 newtons times the cosine of minus 55 degrees. That's 91.77 newtons. You remember, you could also have defined the angle for dog A according to the customary way of finding angles, which would be to start at the x-axis and go counterclockwise around. And you would have found an angle of 305 degrees going that way. And you could have put that in also because the cosine of 305 degrees is the same as the cosine of negative 55. So you would have ended up with 91.9 or 91.77 either way. The y component of vector A, not surprisingly, is going to be negative because, of course, the projection on the x-axis of vector A is going to be below the origin, or negative y territory. And so that's going to be A times the sine of theta A. So that's 160 newtons times the sine of minus 55, or the sine of 305, whichever you prefer. And that's negative 131.1 newtons. So those are the x and y components of vector A. For vector B, or dog B, the vector for dog B, the x component is just the magnitude of B, that would be the force, times cosine theta B, which is the angle we just found up here. So that's 200 newtons times cosine of 30, that's 173.2 newtons. For the y component of the vector for dog B, that's going to be the magnitude, in other words, the force of the dog pulling, times the sine of theta B. So that's going to be 200 newtons times the sine of 30, which would be 100 newtons exactly. And the x component for the vector for dog C would be the magnitude, that is the force with which dog C is pulling, times cosine theta C. So that's 140 newtons times the cosine of 145, or negative 114.7 newtons. And Cy is just, again, the magnitude of the force for dog C times the sine of theta C. So that's 140 newtons times the sine of 145, which is 80.30 newtons. Okay, then you can just add them up to find the resultant. The x component of the resultant would be the x component of A plus the x component of B plus the x component of C. And so that is 91.77 plus 173.2 plus minus 114.7, and that's 150.3 for the x component of the resultant. The y component is just the y component of the, that is the y component of the resultant is just the y component of A plus the y component of B plus the y component of C. which again we found up here. So that's negative 131.1 plus 100 plus 80.30. And that gives you 49.2. So the resultant is 150.3 times the unit vector I, because that's the x direction, unit vector for the x direction, plus 49.20 times unit vector j. And the units would be in newtons. So there's your equation for the vector of the resultant of A, B, and C. And now the direction of the resultant would be the inverse tangent. That is, in other words, the angle whose tangent is the y component over the x component. So that's 49.2 over 150.3, or an angle of 18.13 degrees, according to the conventional way of measuring angles, which is going counterclockwise from the x-axis. And the way this problem stated it, that would be 18.13 degrees north of east, in other words. Dog D, if he is going to pull with enough force to and in a direction to counteract that resultant, that means that the vector for dog D has to have the same magnitude but the opposite direction. Okay, remember with vectors we indicate direction as positive or negative. So that means if the resultant was positive 150.3 I plus positive 49.20 J, then dog D, his vector must be negative 150.3 I plus negative 49.20 J. Okay, so that's the vector for dog D, the equation. The magnitude of the vector, that is, in other words, the force with which dog D is pulling, would be the square root of the x component squared plus the y component squared. So that's square root of minus 150.3 squared plus negative 49.20 squared, which is 158.1 newtons. So dog D must be pulling with a force of 158.1 newtons, and the direction would be 18.13 degrees south of west. If the resultant was north of east, then dog D must be pulling at the same angle, but south of west instead of north of east. If you wanted to look at the angle, remember, south of west would be an angle basically like this, 18 degrees south of west. If you wanted to define the angle according to the normal way of doing things, you would take this as the angle. So that's 180 plus 18.13, or 198.13 for the angle. So there's your magnitude and direction for dog D. All right, so hopefully that makes sense now. It was a lot of work, but you'll find after doing a few examples of these problems, I think you'll find, as I have, as you can see, I've made a few mistakes here and there. Your main problem is going to be with bookkeeping, just keeping straight what's what. Not so much a problem with how to do things, but just keeping straight, making sure you're using the sine when you should be using the sine, and the cosine when you should be using the cosine, and that sort of thing. Okay, we've got another example almost immediately here on the tails of that example, and that is find the magnitude of C, that is vector C, that satisfies the equation 2 times vector A minus 6 times vector B plus 3 times vector C equals 2 times the unit vector J. That right there looks terrible because you've got, well, you're doing all kinds of things. You're multiplying by 2, you're multiplying by 6, you're subtracting this, you're multiplying by 3, and J is a unit vector in the y direction. It's not a whole vector. So it might be very confusing at first. But if you sort of take it step by step and sort of take things apart and look at them in terms of their components, it becomes a lot easier. And also they're giving you the fact that vector A is equal to unit vector I minus 2 times unit vector K, and vector B is equal to negative unit vector J plus 1/2 unit vector K. I've written the 1/2 as 0.5 just because I don't like writing fractions when I'm doing math. I try to avoid it if I can. Now, if something like 1/3, then sometimes writing 1/3 is better than writing 0.333 or 33333 or whatever. But if it's 1/2, I'm going to write 0.5. So we've got, again, 2 times vector A minus 6 times vector B plus 3 times vector C equals 2J. What I'm underlining here, vector C, that's what we need to solve for because that's what we want to know. We've got vector A and vector B in terms of I and J and K. And so we can write those terms in terms of the unit vectors. We can just write those in for A and B. So 2 times vector A is the same as saying 2 times unit vector I minus 2 times unit vector K. And then you just distribute that 2 over it and put it all together. And then minus 6 times vector B is the same as saying minus 6 times the quantity negative unit vector J plus 0.5 unit vector K, plus 3 times vector C equals 2 times unit vector J. So distribute the 2 over the quantity in parentheses, you get 2 times unit vector I minus 4 times, because it's 2 times 2, unit vector K, plus 6, because it's negative times negative. So it's going to be plus 6 times unit vector J minus, and I almost missed this, 6 times 0.5 is 3 times unit vector K, plus 3 times vector C equals 2 times unit vector J. So consolidate the similar terms on the left-hand side. You end up with 2 times unit vector I minus 7 times unit vector K plus 6 times unit vector J plus 3 times vector C equals 2J. Take everything I'm underlining, that is all the stuff in terms of I and J and K, over to the other side so that you can get the 3 times unit vector C alone, because C is what you're trying to solve for. You get 3 times vector C equals negative 2 times unit vector I minus 4 times unit vector J, because it's when you take this plus 6 over to the other side, it becomes a negative. And so you end up with 2 minus 6. So that's negative 4 times unit vector J plus 7 times unit vector K is equal to 3 vector C. So for vector C, just divide all that by 3. So this divided by 3, you end up with negative 2/3 unit vector I minus 4/3 unit vector J plus 7/3 unit vector K. And that would be the equation for vector C. In this case, I used the actual fractions because, again, 2/3 is not a rational fraction. It goes on and on and on. So it's rather than rounding it off, I just put 2/3. And the same with 4/3 and 7/3. So the components are going to be, the x component of vector C would be negative 2/3. The y component of vector C is negative 4/3. And the z component of vector C is positive 7/3. If you want the magnitude, because it asked up here at the top for the magnitude, the magnitude would be just the square root of the x component squared plus the y component squared plus the z component squared. Take the square root of it. And so that is negative 2/3 squared plus negative 4/3 squared plus 7/3 squared. Take the square root of it. And that comes out to the square root of 7.6664. I eventually did have to round off and use decimals. And that's 2.769. That's the magnitude. They didn't give any units here, so it's just a number. Normally we would want to use units. Okay. So that's that's a problem that seemed really difficult at first, but once you know what the vectors are equal to in terms of their unit vectors, it's really just algebra from that point on. And so it's not as hard as it looks at first glance. In the next example, we have a cross-country skier who's going all over the place, and we want to find out displacement vectors for the skier. In this displacement of the skier, we've got a cross-country skier who starts at the lodge and goes 5 kilometers north, then 3 kilometers west, and then 4 kilometers southwest, and then rests. What is the total displacement from the lodge at the resting point, presumably? How far and what direction would the skier have to go to return? Okay, so essentially to return, it's just the sort of the inverse of the displacement vector. So once we find the displacement vector, saying how far and what direction to return should be pretty easy. So we're going to define the lodge as the origin, since all of these distances, well, the original distance was measured from the lodge, and then all the other distances were measured from the last step. We're going to define, as usual, east will be the positive x direction, and north will be the positive y direction. That means that west will be the negative x direction, and south will be the negative y direction. And the only other direction that's mentioned here is southwest. Southwest would be halfway between south and west. West is 180 degrees and south is 270 degrees. If we've got like so. If east is 0 degrees, then north would be 90 degrees, west would be 180 degrees, and south would be 270 degrees. And going around to east again would be 360 degrees. Southwest is halfway between west and south. So that would be halfway between 180 and 270, which is 225. You can find that either by saying, well, the difference here is 45 or is 90 degrees. The difference between 180 and 270 is 90 degrees. Half of that is 45. So just add 45 to 180 or subtract 45 for 270. Either way, you get 225 degrees. Or you could take the average, 180 plus 270 divided by 2. And again, you get 225. So that's southwest is 225 degrees in terms of our normal Cartesian coordinates. According to the problem, there are 3 segments to the journey. There's the 5 kilometers north, 3 kilometers west, and 4 kilometers southwest. So you would want to divide up the 3 segments of the journey and find the vector components for each of them. The displacement for the total journey between the lodge and the resting point would be the basically the sum of the vector for the first segment plus the vector for the second segment plus the vector for the third segment. For the first segment, that vector, or the magnitude of that vector, is going to be equal to the x component for the vector plus the y component for that segment of the journey. And so the x component for the first segment will just be the magnitude of the first segment, which is the distance, times cosine of the angle for the first segment. Okay, it says 5 kilometers north. So the magnitude is 5 kilometers, and north is 90 degrees. So cosine of 90. And that gives you 0 kilometers because the cosine of 90 is 0. The y component for the first segment is going to be the magnitude of the first segment, which again is 5 kilometers, times the sine of theta for the first segment, the sine of the angle of the first segment, which is 90 degrees. So it's 5 kilometers times the sine of 90 degrees. Sine of 90 is 1, so that gives you 5 kilometers. Okay, I see we're about at the time for the end of the second segment, so I'm going to stop there and we'll continue on with the rest of the problem in the third segment. So I'll be right back.